At 0630 hours on November 8, 1942, American soldiers crouched behind sand dunes near Fadala Beach in Morocco, watching enemy tanks roll toward their positions. Many were barely out of basic training and holding weapons they had never seen before yesterday. The weapon was a metal tube about 4.5 feet long. Someone had called it a bazooka. The soldiers had received them the night before the invasion with no instructions, no training, and no idea how to fire them. Sergeants handed out the launchers and rockets and told men they could stop a tank. That was all the guidance anyone received. The morning air was cold and damp. Salt spray from the Mediterranean mixed with the acrid smell of smoke from burning vehicles on the beach. Machine gun fire echoed across the sand, the distinctive chatter of American .30 caliber guns answered by the slower rate of enemy weapons. Somewhere, offshore, naval guns boomed as destroyers provided covering fire for the landing troops. French Renault tanks were grinding across the beach toward the American landing zone. The infantry had no artillery support, no anti-tank guns, just rifles, grenades, and this strange tube that supposedly packed the punch of a field cannon. The tanks were 400 yards away and closing. Their tracks churned the wet sand. Turrets traversed slowly, guns seeking targets among the scattered American positions. Soldiers shouldered the launchers, feeling their unfamiliar weight, pointed them at the tanks and wrapped their fingers around the triggers. They squeezed. Nothing happened. They pulled the triggers again. Harder. Still nothing. The tanks were 300 yards away now, engines roaring like angry mechanical beasts, turrets traversing toward their positions, dark muzzles of the guns swinging in their direction. Men checked the rockets, made sure they were seated properly in the tubes. They traced the wires with their fingers, tried to remember what little. They had been told about the weapons. They pulled the triggers again, yanking them back with desperate force. The launchers did not fire. Soldiers threw the useless weapons into the sand and ran. Tank machine guns opened up, kicking up geysers of wet sand as men dove into shallow trenches. Bullets cracked overhead. They pressed themselves into the earth, hearts pounding, lungs burning, alive only because the tank commanders had moved on to other targets. What nobody on that beach knew was that they were holding weapons that would fail American soldiers across North Africa for the next 6 months. Weapons that were supposed to change infantry warfare forever, but instead left men defenseless against enemy armor. Weapons that the Germans would capture, copy, and turn into something far more deadly than Americans ever imagined. This is the story of how the United States Army sent its soldiers to fight tanks with weapons that would not fire, and how that catastrophic failure, that betrayal of the men who depended on their equipment, forced a complete redesign that eventually made the bazooka one of the most important infantry weapons of World War II. The origins of the bazooka trace back to 1918, when a young physicist named Robert Goddard demonstrated a tube-launched rocket to the United States Army Signal Corps at Aberdeen Proving Ground in Maryland. The demonstration took place on November 6, 1918, just 5 days before the armistice ended World War I. With the war over, military interest in rocket weapons evaporated. Goddard's prototype was filed away and forgotten. For the next 2 decades, the United States Army gave little thought to man-portable rocket launchers. The infantry had their rifles, their machine guns, and their artillery. Tanks were new, ungainly contraptions that moved slowly and broke down frequently. The idea that infantry might need a dedicated anti-tank weapon seemed unnecessary. Then the German Wehrmacht showed the world what tanks could really do. In September 1939, German panzer divisions crushed the Polish army in less than 4 weeks. Tanks swept through defensive positions, encircled infantry formations, and rendered traditional battlefield tactics obsolete. The following spring, the same tactics destroyed the French army and drove the British Expeditionary Force into the sea at Dunkirk. By the summer of 1940, German armor dominated Europe. The United States Army watched these developments with growing alarm. American infantry had almost nothing that could stop a modern tank. The standard anti-tank weapon was the 37mm gun. It was heavy, required a crew of several men to operate, and had to be towed into position behind a vehicle. Setting it up took precious minutes that infantry under attack simply did not have. And against the new generation of German armor with thicker plates and improved design, the 37mm was increasingly ineffective. Infantry soldiers also had anti-tank grenades with shaped charge warheads that could penetrate armor, but these grenades required a man to get within throwing distance of a tank, usually about 30 yards, against a vehicle bristling with machine guns and crewed by men specifically watching for infantry threats. Approaching that close was essentially a suicide mission. The army had experimented with rifle grenades, launching shaped charges from the end of a rifle barrel using blank cartridges. But the most effective warheads were too heavy for this method. The recoil would injure the shooter, or the projectile would not fly far enough to be useful. Major Leslie Skinner of the Army Ordnance Corps had been working on rocket-propelled weapons since the mid-1930s. A career ordnance officer with a talent for unconventional thinking, Skinner had become convinced that rockets were the answer to the anti-tank problem. He had experimented with attaching small rocket motors to grenades, trying to extend their range beyond what human muscle could achieve. But Skinner could never solve the fundamental problem. The shaped charge warheads capable of penetrating tank armor were simply too heavy. The M10 grenade, the Army's most effective anti-tank munition, weighed nearly 4 pounds. It packed enough explosive power to burn through 4 inches of steel plate. But nobody could throw a 4-pound object with enough accuracy to hit a moving tank, and the grenade was far too heavy to launch from a rifle. The only idea anyone had for delivering the M10 was for some poor sap to physically run up to an enemy tank and place the grenade directly against its armor. Army training manuals actually described this technique. The illustrations showed a soldier sprinting toward a tank, dodging machine gun fire and slapping the grenade against the hull before diving for cover. That such instructions were printed and distributed tells you how desperate the situation had become. In early 1942, Skinner received a new assistant. Lieutenant Edward Ewell was fresh out of Lehigh University in Bethlehem, Pennsylvania, where he had graduated with honors in engineering physics. He had joined the Army shortly after Pearl Harbor and been assigned to the Ordnance Corps based on his technical background. UHL was 24 years old, idealistic and eager to contribute to the war effort. Skinner assigned him a seemingly impossible task: design a way for a single infantryman to deliver a 4-pound shaped charge grenade to a target accurately and safely. Do it quickly. The Army needed this weapon yesterday. UHL threw himself into the problem. He read everything he could find about rockets, shaped charges, and launcher design. He sketched concepts, calculated trajectories, and built small-scale models. Every design had some fatal flaw. The M10 grenade was too heavy for any existing launcher system. Attaching a rocket motor could propel it far. Enough, but the exhaust would burn the soldier firing it. Goddard had worked on tube-launched rockets back in 1918, but his designs required complex mechanical systems to protect the operator. The Army needed something simple, something that could be manufactured quickly and used by soldiers with minimal training. UHL struggled for weeks. He tried different rocket motor configurations. He experimented with heat shields and deflectors. Nothing worked. Then one afternoon in the spring of 1942, Ewell was walking across the Aberdeen Proving Ground complex when he passed a scrap pile. The military dumped all sorts of discarded equipment there, everything from damaged vehicles to obsolete weapons to industrial debris. Ewell had walked past this pile dozens of times without giving it a thought. But this time, something caught his eye. A metal tube was lying among the debris. It was about 5 feet long and appeared to be approximately 60 millimeters in diameter. Wall stopped. He stared at the tube. 60 millimeters. That was the exact diameter of the M10-shaped charge grenade they were trying to launch. The solution crystallized in his mind. Put the rocket-propelled grenade inside the tube. Fire it from a soldier's shoulder. The tube would contain and direct the exhaust safely out the back behind the soldier. The operator would be protected from the burning gases. The whole assembly would weigh less than 15 pounds. One man could carry it, aim it, and fire it. Ewell grabbed the tube from the scrap pile and practically ran back to the workshop. He found Skinner and explained his idea in a breathless rush. Skinner listened, asked a few questions, and nodded. It was worth trying. The prototype came together quickly. Ole and Skinner attached the tube to a simple wooden shoulder stock salvaged from a broken rifle. They added a battery-powered ignition system, 2 dry cell batteries wired to send an electrical current through contacts in the tube. To ignite the rocket motor, a basic iron sight, little more than a metal loop, was mounted on top for aiming. The first test firing sent a rocket into the Potomac River. It worked. The rocket flew straight and true. The exhaust vented safely out the back of the tube. The soldier firing it, a nervous volunteer who had been promised extra leave if he survived the test, was completely unharmed. Skinner and UL refined the design over the following weeks. They adjusted the tube length to ensure the rocket motor burned out before the projectile exited the front. They improved the sights. They worked on the battery connections to ensure reliable ignition. In May of 1942, they brought their prototype to Aberdeen Proving Ground for a competitive trial against other anti-tank weapon designs. Several contractors had submitted concepts. There were spigot mortars, recoilless rifles, and various launcher configurations. The Army wanted to see which design worked best. On the morning of the demonstration, Ole and Skinner discovered a problem. They had forgotten to install proper sighting equipment. The prototype had only a crude metal loop that was barely adequate for testing, certainly not suitable for demonstrating to senior officers. Skinner solved the problem with characteristic pragmatism. He found a wire coat hanger, bent it into a rough approximation of a proper sight, and attached it to the tube. The improvised sight was ready minutes before the test began. Despite this last-minute improvisation, the launcher was the only weapon in the trial that could consistently hit a moving tank. The spigot mortars were inaccurate. The recoilless rifles were too heavy. Only the tube launcher demonstrated the combination of accuracy, portability, and effectiveness that the Army needed. Brigadier General Gladian Marcus Barnes, head of Ordnance Research and Development, happened to be passing by the test range with other senior officers. They heard the distinctive whoosh of the rockets and saw the flames jetting from the back of the tube. Curious, they came over to investigate. Skinner saw his opportunity. Taking a calculated risk, he handed the launcher to General Barnes and offered to let him take a shot at the target tank. Barnes accepted. He shouldered the weapon, aimed through the coat hanger sight, and fired. The rocket flew straight and true. It struck the target tank dead center. Barnes fired again, another hit. The demonstration so impressed senior Army leadership that within an hour, the order for 5,000 launchers had been approved, endorsed by General George C. Marshall, Chief of Staff of the United States Army. When the weapon was demonstrated, an officer remarked that it looked like the musical instrument played by Bob Burns, a popular radio comedian of the era. Burns had created a novelty horn made from pipes and a whiskey funnel. He called it a bazooka. The nickname was immediately adopted by the soldiers at Aberdeen. The official designation was the M1 rocket launcher, but from that day forward, everyone called it the bazooka. General Electric received the production contract on May 20th, 1942. The company was given 30 days to deliver 5,000 launchers. Engineers worked around the clock, setting up assembly lines, training workers, and establishing quality control procedures. They finished with 89 minutes to spare. The bazooka would go on to become one of the most widely produced American weapons of the war. But those first 5,000, rushed out the door in a frantic race against time, carried flaws that would cost American lives. The Army shipped the bazooka into production with the urgency of a nation fighting for survival. By the summer of 1942, launchers were rolling off assembly lines at General Electric's Bridgeport plant. The rockets, designated M6 high-explosive anti-tank rounds, were being manufactured by the E.G. Budd Company. Everything looked promising on paper. But speed came at a cost that would not become apparent until soldiers tried to use the weapons in combat. The M1 launcher was built from sheet metal tubing that had been pressed and welded into shape. Under normal circumstances, each tube would have been checked with precision bore gauges to ensure consistent internal diameter. The rocket had to fit precisely inside the tube. Too tight, and the rocket could stick. Too loose, and the exhaust gases would escape around the projectile instead of propelling it forward. But there were no bore gauges. The production contract had been signed so quickly that nobody had time to manufacture the specialized measuring equipment needed for quality control. Tubes came off the production line with variations of several thousandths of an inch. This might seem insignificant. It was not. A rocket that stuck inside the tube would continue burning. The pressure would build as the propellant consumed itself. Something would have to give. Usually it was the tube itself which would rupture and send shrapnel into the soldier holding it. Even if the tube held, the soldier would be left with a live rocket jammed in his launcher, burning and ready to explode. Even worse, the steel used for the tubes was substandard. Wartime shortages meant that manufacturers could not always obtain the specific alloys called for in design specifications. They substituted whatever was available. The steel that went into the first bazookas was chosen for availability rather than quality. On hot days, when the sun heated the metal tubes to extreme temperatures, the rocket propellant would burn faster than designed. The increased pressure combined with the weakened steel created a lethal combination. Tubes could rupture even when the rocket did not stick, simply because the hot propellant generated more pressure than the tube could contain. The battery ignition system added another layer of problems. The M1 used 2 standard dry cell batteries housed in the wooden shoulder stock. These batteries were supposed to send an electrical current through wires to contacts inside the tube. When the trigger was pulled, the circuit would complete, current would flow, and the rocket motor would ignite. But dry cell batteries are sensitive to temperature and humidity. In cold weather, the chemical reactions that produce electricity slow down. The batteries lose power. In extreme cold, they can become completely inert. In extreme heat, the chemicals can become volatile. The batteries can leak, corroding the contacts and wires that carry the current. In humid conditions, the salt air and moisture that are endemic to beach landings and tropical environments, the battery contacts corrode. A thin layer of oxidation builds up on the metal surfaces. This oxidation acts as an insulator, preventing the current from flowing even when the batteries are fully charged. The M6 rocket itself was notoriously unreliable. The ignition system used an electrical contact on the nose of the rocket that had to mate precisely with a contact inside the launcher tube. If these contacts were dirty, corroded, or misaligned by even a fraction of a millimeter, the circuit would not complete. The rocket would not fire. The rocket motor was equally problematic. The solid propellant was sensitive to temperature extremes. The designers had specified that rockets should not be fired at temperatures below 0 degrees Fahrenheit or above 120 degrees Fahrenheit. Below freezing, the propellant burned too slowly. The rocket would not develop enough velocity. It would fall short of its target, wobbling through the air before plummeting harmlessly to the ground. Above 120 degrees, the propellant burned too fast. The increased pressure could cause the tube to rupture. In the North African desert, where Operation Torch would take American forces, temperatures could swing from near freezing at night to well over 100 degrees during the day. The bazooka was being sent to fight in exactly the conditions that would cause it to fail. And finally, there was the warhead itself. The M6 rocket had a pointed nose designed for aerodynamic efficiency. When the rocket struck armor at a perpendicular angle, the shaped charge detonated properly and burned through the steel. But when the rocket struck at an angle, as it often did in the chaos of combat, the pointed nose could deflect. Instead of detonating against the armor, the rocket would ricochet away. None of these problems were discovered before the bazooka went to war. There was no time for extended testing, no opportunity for soldiers to train with the weapon and report its limitations. The army needed an anti-tank weapon, and the bazooka was it. Everything else would have to be figured out later. In November 1942, Operation Torch brought American forces to North Africa for the first time. It was the largest amphibious invasion in history to that point, with over 107,000 troops landing at Casablanca, Oran, and Algiers. The operation was supposed to drive German and Italian forces from North Africa and open the Mediterranean to Allied shipping. Among the equipment hastily loaded onto the transport ships were crates of M1 Bazookas and M6 rockets. The weapons had been manufactured just weeks earlier. They had never been tested in combat conditions. Many had never been test-fired at all. On the night before the invasion, General Dwight Eisenhower learned something that shocked him. A subordinate informed him that none of the troops had received any training on the bazooka. Not a single soldier in the entire invasion force knew how to load, aim, or fire the weapon they were carrying. The launchers had been shipped with minimal documentation. Some crates included brief instruction sheets, others did not. The men who would carry these weapons into battle had never seen them before they boarded. The transport ships, they had no idea what they were supposed to do with them. Eisenhower could do nothing. The invasion was hours away. There was no time to conduct training, no opportunity to familiarize soldiers with the new equipment. The bazooka would receive its combat debut in the hands of men who did not know how to use it. The landings at Fedala, Safi, Port Laouti, and other beaches along the Moroccan and Algerian coast were chaotic. Soldiers scrambled ashore under fire, dragging equipment through the surf, seeking cover wherever they could find it. Many discovered for the first time what equipment they were carrying when they opened their assigned crates. Men expected to find rifles, machine guns, or ammunition. Instead, they found metal tubes and unfamiliar rockets they did not recognize. There was no time to read instruction sheets, if any had been included. There was only the chaos of combat, the crack of bullets, the boom of explosions, and the desperate need to find something that could stop the enemy vehicles that were already engaging the landing forces. In the confusion, soldiers attempted to use their bazookas against enemy positions. The results were disastrous. Rockets failed to fire, tubes jammed, batteries died in the cold morning air or corroded from exposure to salt spray. Soldiers pulled triggers and heard nothing but silence. Some men were injured when stuck rockets detonated inside the tubes. The sheet metal ruptured, sending jagged fragments into hands and arms and faces. Other soldiers simply abandoned the weapons as useless weight, discarding them on the beach and picking up rifles from fallen comrades instead. Field reports documented the chaos. Bazooka teams encountered enemy armor and found their weapons would not fire. Loaders checked connections and reseated rockets while gunners squeezed triggers again and again with no result. Machine gun fire cut down men before they could attempt a third shot. Others threw their launchers away. Just as stuck rockets detonated, suffering wounds from weapons that were supposed to protect them. The bazooka's combat debut was a complete failure. Not a single confirmed tank kill was achieved by bazooka fire during the Operation Torch landings. The weapon that was supposed to revolutionize infantry warfare had proven itself unreliable, dangerous to its own operators, and ineffective against enemy armor. By the time Operation Torch concluded and American forces pushed into Tunisia to face the German Afrika Korps, field reports were flooding back to Army ordnance. The message was unanimous and damning. Weapon unreliable, rockets defective, troops have no confidence in bazooka. Do not send more until problems are fixed. The reports were filed, committees were formed, studies were commissioned, but the war did not wait for bureaucratic processes to produce solutions. In February 1943, those same undertrained American forces with their unreliable bazookas met the German Afrika Korps for the first time at a place called Kasserine Pass. It would become one of the most humiliating defeats in United States military history. Field Marshal Erwin Rommel, the legendary Desert Fox, launched his offensive on February 14, 1943. German Panzer IV medium tanks and massive Tiger heavy tanks rolled through the mountain passes of western Tunisia, smashing into American defensive positions. The American troops were green, inexperienced, and poorly led by commanders who had never faced German armor in combat. The soldiers at Kasserine had received their first shipment of bazookas on February 12th, just 2 days before the German attack. They had no time to train, no time to practice, no time to understand the weapon's capabilities or limitations. Most had not even opened the crates when the first German tanks appeared. Infantry units attempted to engage the advancing armor with their new weapons. The results were catastrophic. Rockets failed to fire despite multiple trigger pulls. Soldiers checked connections, reseated projectiles, and tried again with no success. Enemy tanks continued their advance, turrets traversing toward American positions, machine guns cutting down anyone who exposed themselves. When rockets did fire, many struck the heavy frontal armor of Tiger tanks and deflected harmlessly. The pointed M6 warheads bounced off the sloped steel without detonating. Soldiers watched in horror as their shots ricocheted away, leaving nothing but scratches on enemy armor. Other rockets jammed in tubes. Men found themselves holding launchers with live rockets stuck inside, burning propellant building pressure with nowhere to go. Some threw the weapons away in time, others were not so fortunate. The tubes ruptured, sending fragments into the soldiers who had trusted their equipment to save them. Field reports documented that of the rockets fired during the Kasserine engagement, the majority failed to ignite at all. Those that launched often failed to penetrate German armor. The few that actually damaged enemy vehicles did so through lucky hits on tracks, engine compartments, or other vulnerable points. Not a single Tiger tank was confirmed destroyed by bazooka fire. The disaster at Kasserine Pass cost the Americans over 6,000 casualties. More than 180 tanks were lost. Thousands of soldiers were captured. The Germans drove the American forces back over 50 miles before finally running out of momentum. Among the vast quantities of American equipment captured by the Germans during Operation Torch and the subsequent Tunisian campaign were entire crates of bazookas that had never been opened. The weapons sat in warehouses and supply dumps, still packed in their original shipping containers, unused and untested. Now they belonged to the Wehrmacht. Those captured bazookas would have far-reaching consequences. German intelligence immediately recognized the value of what they had. Found. The rockets were shipped back to Berlin for analysis. Engineers at Wehrmacht ordnance facilities dismantled the launchers and rockets, studied the shaped charge warhead design, analyzed the construction techniques, and reached a conclusion. The concept was brilliant. The execution was flawed, but the concept was absolutely brilliant. German engineers set to work immediately. They would copy the bazooka, but they would make it better, much better. The German version was designated Raketenpanzerbuchs. Soldiers quickly gave it a more memorable name: Panzerschreck, tank terror. Instead of the American 60mm warhead, the Germans used 88mm. The larger diameter meant a bigger shaped charge, which meant more penetrating power. The Panzerschreck could burn through over 100mm of armor, nearly twice what the American bazooka could achieve. The Germans also fixed the ignition problem. They replaced the troublesome battery system with a spring-loaded magneto. When the soldier pulled the trigger, a mechanical system generated its own electrical current. No batteries to die, no contacts to corrode. The weapon would fire in any weather, any temperature, any conditions. The German rocket motor was also more powerful, which created a new problem. The propellant continued burning for about 2 meters after the rocket left the tube, creating a jet of flame that would burn the operator. The Germans solved this by adding a sheet metal blast shield to protect the shooter's face. They also issued protective gloves, ponchos, and gas masks, with the filters removed to operators using the weapon. By late 1943, the Panzerschreck was in mass production. German infantry finally had a portable weapon that could destroy Allied tanks at range, and they had the Americans to thank for the basic design. The irony was bitter. The weapon that had failed American soldiers in North Africa had been captured, improved, and turned against them. The very tanks that American bazookas could not stop would now face an improved version of their own weapon in German hands. American soldiers who had cursed their unreliable bazookas would soon encounter the Panzerschreck on battlefields across Italy and France. They would learn what it felt like to be on the receiving end of a weapon that actually worked. Back in the United States Army Ordnance scrambled to fix the problems that had made the bazooka a liability instead of an asset. Field reports from North Africa and Tunisia were devastating. Senior officers touring the Tunisian front after the fighting ended could not find a single soldier who could confirm that the M1 Bazooka had actually stopped an enemy tank in combat. The promise of a man-portable tank killer had proven hollow. Every claim made for the bazooka had been contradicted by combat reality. The Army suspended further issue of the M1 Bazooka in May 1943. Production continued at reduced rates, but the launchers were held back for modifications and improvements. Engineers at Aberdeen Proving Ground and Ogden Arsenal began a systematic analysis of every failure mode. Reports of rockets sticking and prematurely detonating in launch tubes had reached Army ordnance from multiple sources. At Aberdeen, Engineers tried various solutions. They wrapped wire around the rear section of tubes to reinforce the sheet metal against ruptures. They developed bore slug test gauges to ensure rockets would not catch inside the tube. They rejected any launcher that failed the new dimensional tolerances. The rocket received extensive redesign. The problematic nose contact was eliminated in favor of a more reliable ignition system. The pointed warhead that had bounced off German armor was replaced with a blunted, rounded nose that would detonate on impact at low angles instead of deflecting. This new rocket was designated M6A3. The battery ignition system was identified as a fundamental flaw. Engineers began developing a magneto-based system, inspired by reports of the German improvement, that would generate its own electrical current without relying on expendable batteries. The magneto used a spring-loaded mechanism that created current when the trigger was pulled. The modified launcher was designated M1A1. It featured the reinforced tube, improved sights, and better protection against backblast for the operator. Small numbers were ready by July 1943, just in time for the Allied invasion of Sicily. Operation Husky, the invasion of Sicily, began on July 9, 1943. It was the first Allied invasion of European territory in the war, a stepping stone toward the eventual liberation of Italy and the assault on Fortress Europe. American paratroopers from the 82nd Airborne Division jumped into the night sky over Sicily as part of an ambitious plan to secure key positions before the beach landings. Colonel James Gavin, commander of the 505th Parachute Infantry Regiment, led his men into darkness. The drop was a disaster. High winds scattered the paratroopers across 60 miles of Sicilian countryside. Most landed far from their intended objectives. Small groups of soldiers found themselves isolated behind enemy lines, surrounded by Italian and German forces with only the weapons they had carried in their jump. Gavin himself landed in an olive grove with no idea where he was. He gathered what men he could find, eventually assembling a force of about 200 paratroopers from various units scattered across the Sicilian countryside. They moved toward what he hoped was the American objective. Instead, he found himself at a place called Piazza Ridge, directly in the path of the Hermann Göring Panzer Division. The German tanks attacked on the morning of July 10th. Tiger tanks led the assault, their massive 88mm guns blasting American positions. The 60-ton behemoths advanced with deadly confidence, knowing that lightly armed paratroopers should pose no threat to their 4-inch thick frontal armor. Gavin's men had no heavy weapons. Their artillery had been scattered across the island or lost in the drop. All they had were rifles, machine guns, and a handful of the new M1 bazookas. What happened next would determine whether the bazooka could ever become a reliable infantry weapon. The paratroopers positioned their bazooka teams on the reverse slope of the ridge, waiting for the Tigers to crest the hill. The men had practiced with the M1 in England before the invasion. They knew the weapon better than the untrained soldiers at Kasserine. They trusted it, as much as any soldier could trust equipment that had failed so spectacularly just months before. The lead Tiger appeared over the crest of the ridge. Gunners shouldered their launchers, aimed for center mass, and fired. The rockets launched. They flew straight and true. They struck the Tiger's frontal armor and detonated with sharp cracks. The Tiger kept coming. The M1A1 could penetrate about 3 inches of armor. The Tiger's front plate was 4 inches thick. The rockets had detonated properly, had burned craters into the steel, but had not penetrated to the interior. The tanks were damaged but not destroyed. Bazooka teams reported similar results throughout the day. The improved rockets fired reliably. They hit their targets. They detonated on impact instead of bouncing off. But against the heavy armor of the Tiger tanks, they simply were not powerful enough. Still, the improvement in reliability made a critical difference. At Piazza Ridge, the bazookas fired when soldiers pulled the triggers. They might not have killed the Tigers outright, but they damaged tracks, destroyed optics, and wounded crew members who exposed themselves. The constant harassment forced the German tanks to proceed more cautiously, to button up their hatches, to lose the situational awareness that made armor so deadly. Combined with a few pack howitzers that arrived as reinforcements and naval gunfire from offshore destroyers, Gavin's outnumbered paratroopers held their position. The Hermann Goering Division, stopped by a handful of paratroopers with light weapons, withdrew to regroup. The Sicily campaign also produced one of the bazooka's most improbable successes. During fighting near Gela, an M1 A1 team knocked out a Tiger tank with a single shot. The rocket had struck the tank's driver vision slot, the only point on the front armor weak enough for the warhead to penetrate. It was an incredible piece of shooting and an even more incredible stroke of luck. The feat proved that under the right circumstances, with perfect aim and favorable conditions, even the 60mm bazooka could kill a Tiger. But it also demonstrated the weapon's limitations. Soldiers could not count on hitting a 6-inch vision slot in the chaos of combat. They needed more penetrating power, not more luck. By the end of the Sicily campaign, American commanders had a clearer picture of what the bazooka could and could not do. It was effective against light armor, half-tracks, armored cars, and older tank models with thinner armor. It was deadly against fixed positions, bunkers, and machine gun nests. But against the latest German heavy tanks, it was a desperation weapon at best. The feedback from Sicily accelerated development of an entirely new bazooka model. The M9, standardized in October 1943, incorporated every lesson learned from North Africa and Sicily. The new launcher featured a trigger-operated magneto that eliminated batteries entirely. When the soldier pulled the trigger, a spring-loaded mechanism generated the electrical current needed to ignite the rocket. No more dead batteries, no more corroded contacts. The system worked reliably in any climate, from Arctic cold to tropical heat. The M9 could be broken down into 2 sections for easier carrying, a critical improvement for paratroopers who had to jump with their weapons. The 2 pieces connected with a bayonet joint that was quick to assemble and secure in action. The overall tube length was increased to 61 inches, which improved accuracy by giving the rocket more guidance before it left the barrel. The longer tube also ensured that the rocket motor burned out completely inside the launcher, eliminating the danger of the operator being burned by escaping propellant. A new safety system isolated the magneto until the soldier deliberately armed the weapon, preventing accidental discharges that had injured and killed men during training and transport. The folding aperture sight was eventually replaced by a Polaroid optical reflector sight that allowed faster target acquisition. The improved M6A3 rocket with its blunted nose became standard ammunition. It could penetrate up to 4 inches of armor at perpendicular impact and was far more reliable than the early M6 rounds that had failed so catastrophically in North Africa. Production of the M9 and its successor, the M9A1, ramped up throughout 1944. By the time of the Normandy invasion in June, American infantry finally had a man-portable anti-tank weapon they could rely on. The bazooka that landed at Normandy was fundamentally different from the weapon that had failed at Battle of Kasserine Pass. It was the same concept, the same basic design, but every critical component had been improved based on the bloody lessons of those early failures. The soldiers who carried the M9 through the hedgerows of France and into the cities of Germany inherited a weapon that had been paid for in blood. The men who died at Kasserine holding launchers that would not fire had contributed to the redesign that saved lives on later battlefields. In September 1943, Allied forces landed at Salerno on the Italian mainland. The Germans were waiting. Unlike the relatively disorganized Italian defenders in Sicily, the Wehrmacht had prepared killing grounds along the beaches and in the hills beyond. American infantry walked into a firestorm. Infantry units found their bazookas more reliable than those at Kasserine, but still imperfect. Field reports documented that multiple rockets were often required to disable a single enemy vehicle. Some rockets failed to ignite, others struck tanks but failed to penetrate. Still, soldiers reported higher confidence in the improved weapons. The M1A1 fired when they pulled the triggers, even if it could not always stop the heaviest German armor. The fighting at Anzio in early 1944 provided more evidence of both the bazooka's improvements and its continued limitations. Technical Sergeant Van Barfoot of the 45th Infantry Division earned the Medal of Honor in part for his actions with a bazooka against German armor. Earlier that same day, Barfoot had already distinguished himself by single-handedly attacking German machine gun positions, capturing 17 enemy soldiers and killing 8 others. But his day was far from over. When the Germans launched an armoured counterattack later that afternoon, Barfoot took up a bazooka position along the expected avenue of German advance near Carano. 3 Tiger tanks appeared, grinding toward American positions. The massive 60-ton vehicles churned across the Italian countryside, their 88mm guns seeking targets among the American lines. Barfoot took up an exposed position directly in the path of the advancing armor. He waited until the lead Tiger was within 75 yards, close enough to ensure accuracy, then fired. His rocket struck the tank's track, destroying it and immobilizing the massive vehicle. As the crew attempted to dismount, Barfoot engaged them with his Thompson submachine gun, killing 3. The other 2 Tigers, seeing what had happened, changed direction and withdrew, rather than risk the same fate. Barfoot's action demonstrated what a skilled soldier could accomplish with the improved bazooka, but it also showed the weapon's limitations. He had aimed for the track because he knew his rocket could not penetrate the Tiger's frontal armor. He had achieved a mobility kill, not a destruction. The Tiger could potentially be repaired and returned to action. Still, keeping a Tiger out of a battle was a significant achievement. American infantry learned to measure success differently. You did not need to destroy a tank to defeat it, immobilizing it, blinding it, forcing its crew to button up and lose situational awareness. All of these counted as victories. The Marines fighting in the Pacific Theater faced different challenges with the bazooka. Japanese armor was generally lighter than German tanks, with thinner armor that the 60mm warhead could penetrate more reliably. But the Pacific environment created its own problems. The humidity and salt air of island warfare was devastating to the battery ignition systems of the M1 and M1A1 bazookas. Contacts corroded within days of arrival in theater. Batteries drained in the tropical heat. Marines who had trained with the weapon in the relatively dry climate of California found that their equipment failed completely in the jungles of Guadalcanal and New Britain. The rocket motors were equally affected. Propellant that performed reliably at Aberdeen Proving Ground often failed to ignite properly in the moisture-laden atmosphere of the South Pacific. When it did ignite, the burning characteristics were unpredictable. Rockets that should have traveled 300 yards sometimes fell short after 50. Marines reported trying to use bazookas against Japanese bunkers, only to have multiple rockets fail to fire in succession. Battery contacts turned green with corrosion despite having been cleaned that morning. Men resorted to grenades and rifle fire, charging positions because their heavier weapons had failed them. The Marines learned to protect their bazookas as carefully as they protected their rifles. They wrapped the launchers in oilcloth. They kept spare batteries close to their bodies to maintain warmth. They cleaned the contacts obsessively, sometimes multiple times per day. These field expedients helped, but they could not overcome the fundamental weakness of the battery ignition design. The arrival of the M9 with its magneto ignition was a revelation for Pacific forces. Marines who received the new launchers in late 1944 reported dramatic improvement in reliability. The magneto did not care about humidity or salt air. It generated its own current, regardless of environmental conditions. On Iwo Jima in February 1945, bazooka teams played a critical role in reducing the fortified positions that honeycombed the island. The Japanese had constructed an elaborate network of bunkers, tunnels, and pillboxes using the volcanic rock of the island. General Tadamichi Kuribayashi had designed a defense in depth, with overlapping fields of fire and mutually supporting positions. Many of these fortifications were resistant to artillery fire and naval bombardment. The 16-inch shells from American battleships barely scratched the reinforced concrete. These positions had to be taken one by infantry assault. The M9 bazooka proved devastatingly effective against these fortifications. A rocket into the firing aperture of a bunker would kill or wound everyone inside. The shaped charge warhead was designed to penetrate armor, but it worked equally well against concrete and stone. Where flamethrowers could not reach, where grenades could not be thrown with sufficient accuracy, the bazooka offered a standoff weapon that could eliminate enemy positions from 30 to 50 yards away. Marines on Iwo Jima used bazookas to systematically reduce Japanese defensive positions that had stopped. Infantry advances. When squads became pinned down by fire from fortified bunkers, bazooka teams moved forward to eliminate the threat. The weapons that had been so unreliable in the humidity of earlier Pacific campaigns now fired consistently, delivering their shaped charge warheads into the narrow apertures of enemy fortifications. The bazooka on Iwo Jima was a different weapon from the one that had failed at Battle and Kasserine Pass. Same basic concept, same tube-launched rocket with a shaped charge warhead, but reliable now. Effective. A weapon that soldiers could trust when their lives depended on it. But the story does not end with a simple triumph. German armor continued to evolve. The Panther tank that American forces encountered in France had frontal armor that exceeded what even the improved bazooka could penetrate. The King Tiger, introduced in late 1944, was virtually immune to bazooka fire from any angle except the thinnest rear armor. American doctrine adapted to these realities. Soldiers learned to aim for side armor, rear armor, tracks, engine decks, and vision ports. They learned to work in teams, engaging tanks from multiple angles to find vulnerabilities. They learned that the bazooka was not a tank killer, but a tank fighter, a weapon that could damage, disable, and distract, even if it could not always destroy. The bazooka found its greatest utility not against tanks, but against the thousands of other targets that infantry faced. Bunkers, pillboxes, machine gun nests, buildings, and fortified positions all fell to bazooka fire. In the hedgerow country of Normandy, soldiers used bazookas to blast holes through the thick earthen walls that had stalled American advances. In the cities of Germany, they destroyed snipers hiding in upper-floor windows. One American pilot found an unconventional use for the weapon. Major Charles Carpenter, an artillery spotter flying an L-4 Grasshopper observation plane, mounted 6 bazookas on his light aircraft. He used them to attack German armor from above, hitting the thin top armor that tanks could not protect. Carpenter was credited with destroying or disabling at least 6 German tanks, including 2 Tigers, earning him the nickname Bazooka Charlie. The lessons of the early bazooka failures were never forgotten. Even as the M9 proved itself in combat, Army Ordnance was working on something bigger. American engineers began developing an 88.9mm launcher, designated T-74, that could match the penetration of the German Panzerschreck. This weapon would become the M20 Super Bazooka, though it arrived too late for World War II. It entered production in 1948 and saw extensive combat in Korea, where it finally gave American infantry a weapon that could reliably penetrate the frontal armor of enemy tanks. The irony was complete. The weapon the Germans had created by copying captured American bazookas had forced the Americans to essentially copy the German improvement. The Panzerschreck's larger caliber had proven the concept. The Super Bazooka was the American response, developed years after the original flawed weapon had cost so many lives. Edward Uhl, the young lieutenant who had found a metal tube in a scrap pile and changed warfare forever, rose to the rank of lieutenant colonel before leaving the army in 1947. He went on to work for the Glenn L. Martin Company and Martin Marietta on guided missile projects. Later, he became president and chairman of Fairchild Industries, where he oversaw production of the A-10 Thunderbolt, an aircraft designed specifically to destroy tanks. He had come full circle from trying to give infantrymen the power to kill armor. UHL died in 2010 at age 92. His obituary mentioned his work on the bazooka only briefly. Few people outside military history circles remembered that a frustrated engineer walking past a junk pile had conceived a weapon that would influence infantry warfare for decades. The bazooka's troubled birth holds lessons that resonate far beyond military history. It is a story about what happens when urgency overwhelms preparation, when weapons are rushed to combat without adequate testing, when soldiers are sent to fight with equipment they have never trained on and do not understand. The men at Kasserine Pass and on the beaches of Morocco were not failed by their own courage or skill. They were failed by a system that prioritized speed over reliability, that shipped weapons without training, that ignored manufacturing quality in the race to meet production quotas. The soldiers who discovered their bazookas would not fire had every right to feel betrayed. They had been given a weapon that was supposed to be their salvation against enemy armor. Instead, it was a liability, a piece of useless metal that might as well have been a rifle without bullets. But the story does not end in failure. The same military that had rushed a flawed weapon into combat also had the capacity to learn, adapt, and improve. The M1 Bazooka that landed at Normandy represented everything the M1 should have been from the start. This is how innovation actually happens in war. Not through smooth development and flawless deployment, but through catastrophic failures that expose fundamental problems. Through soldiers dying because weapons did not work. Through frantic engineering efforts to fix what should have been designed correctly from the start. By the end of World War II, over 440,000 bazookas had been produced. The weapon that had failed so completely in its first combat test had become standard equipment for every American infantry.